So today we are going to be talking about two different topics. The first topic that we're going to be talking about is the concept of source combination. So let's start by looking at voltage sources in series. So I'm going to draw a circuit here. Let's call this voltage source VS1. I'm going to throw a resistor here, R, that has some voltage drop, VR across it. Arbitrarily, I'm assuming the positive polarity terminal to be on the left. I'm going to call this VS2. Also positive polarity on the left. I'm going to call this VS3, positive polarity on bottom. All right, so I'm going to apply Kirchhoff's voltage law around this single loop circuit. So in doing so, I'm going to get the relationship negative VS1 plus VR plus VS2 minus VS3 is equal to 0. Leaving VR on one side of the equal sign by itself, this is going to look like VS1 minus VS2 plus VS3, or the voltage drop across the resistor is some equivalent series voltage of all of those voltage sources added together, as it were. Okay. Now, really what's happening here is that all of our voltage sources that are of the same polarity are being added together, and all of the voltages that are of the opposite polarity are being subtracted from that total voltage. Now, it's a little bit hard to see which voltage sources have the same polarity and all that kind of stuff. And so what I mean by that is if we look at the left-hand side of the circuit for that voltage source VS1, it has the positive polarity terminal on top. Well, the voltage source VS3 has the positive polarity terminal on bottom on the right-hand side of the circuit, yet those two voltage sources actually have the same polarity. How we see that is if we imagined a current flowing around this loop. So this current, as it flows around this clockwise loop, it sees the negative polarity terminal first for VS1 and the negative polarity terminal first for VS3. So that's why they have the same polarity. It sees the positive polarity terminal for VS2 first, which is why that one has the opposite polarity, and which is why we wind up getting VS1 plus VS3, same polarity voltages, minus VS2, the opposite polarity voltage. Okay. So what's an instance where we might connect voltage sources in series? Exactly right. Anytime that you have changed the batteries in a remote or anything like that, you have been placing voltage sources in series. What happens if you put one of the batteries in backwards? Whatever it's connected doesn't work because it's not receiving the correct amount of voltage, because you're effectively canceling out one of the cells if you put one in backwards, right? So if you had something like this, so we're going to look at the terminal voltage here of one battery and then another battery like so, where each of these were AA batteries, so each one represented 1.5 volts. the voltage at the terminal of your battery pack would simply be those two guys added together. I don't know why the screen is doing that. Let me play around with the cable. But if you were to put one of the batteries in incorrectly, so we had plus minus 1.5 here and minus plus 1.5 here, what we would see is effectively no voltage, which means that whatever was expecting to receive that 3 volts isn't going to behave correctly. Okay? So combining voltage sources in series is something that most of us have probably been doing since we were little kids, changing the batteries out in our Game Boys or whatever. Or I don't know, Game Boy for me when I was a little kid, probably DS or something like that for you guys. I honestly don't even know if a DS has replacement batteries, but anyway. It does not? Okay, well, never mind then. Your remote control for your television or something like that. Okay, so voltage sources in series, fairly straightforward. Now let's look at voltage sources in parallel. So let's say that I have a circuit like so. I'm going to use numbers on this guy. Let's make this 10 ohm resistor. Not that it particularly matters. And let's call this the voltage drop across the 10 ohm resistor. Let's make this a 5-volt source over here. And a 5-volt source over here. So in a configuration like this, what's the voltage drop across the resistor? Not a trick question, or it's not supposed to be anyway. Voltage drop. Hmm? Oh, 5. All right. So if we did Kirchhoff's voltage law around this left-hand loop, we'd have negative 5 volts plus V10 is equal to 0, which means V10 is equal to 5 volts. If we did Kirchhoff's voltage law around this right-hand loop, we would have negative V10 plus 5 volts is equal to 0, which means V10 is equal to 5 volts. So effectively, whenever we have two voltage sources in parallel and they are equal value, it's effectively the exact same thing as just having a single voltage source. It doesn't change anything whatsoever, okay? Now, in practice, what's happening is that we are doubling the amount of current that's going to flow through that, in this case, 10 ohm resistor, okay? Because each of those, or I guess a better way to put it would be we're splitting the current draw through that 10 ohm resistor between the two batteries. So we're going to extend the battery life, I guess would be a better way to place that, okay? Now, whenever we have two identical voltage sources like this in parallel, like I said, it doesn't really affect anything. We could treat it as if there were just one. However, what if we had a system like this? So let's say that on this side, I had a 9-volt battery. Here's my 10 ohm resistor. And on this side, I have a 1.5 volt battery. What's the voltage drop across my resistor? just as heads up, this time it is a trick question. So that is a very good question. Okay. In practice, yes, the 9-volt source would wind up sourcing some current to try to overcharge the 1.5-volt battery. Okay. So why, from a circuit analysis perspective, this doesn't work because it breaks Kirchhoff's voltage law, right? So if I write the KVL equation around this path, I would find that V10 is equal to 9 volts. If I write a KVL equation around this path, I would find that V10 is equal to 1.5 volts. And if I write a KVL equation around this path, I would find that 9 volts is equal to 1.5 volts, which doesn't work. The voltage drop across the resistor can't be two different things for two different paths. That's a violation of Kirchhoff's voltage law. So why is our model breaking here? Because we could physically do this rather easily, right? I could go get a 9-volt battery and a AA battery and a resistor and just wire this up. What would happen? Sparks. Probably not a fire, but possibly a fire, depending on the size of the wiring that I use. Okay. So what this model is neglecting is that the wires have some sort of resistance. Okay. So in practice, this very, very small amount of resistance for this wire right here would have about a 7.5-volt drop over it, which means this portion of the circuit would be carrying a very large amount of current, practically almost as much current as the 9-volt source could possibly supply. I don't know what that is going on. So it's not having more resistance, it's having a large voltage drop over it. So the current, the fact that there's a large amount of current flowing through it is going to heat up the wire. The resistance of the wire isn't going to change. So you're very likely going to wind up melting the insulation on the wire if there is any, and you'll probably see sparking and all that kind of good stuff because it's dangerous. So don't do it, but you could. That's when you gauge the wire. Absolutely. Yep. Well, so I'm trying to figure out what's going on with the the projector thing here. So a larger wire, oh my God. Let me try my different. Okay, well, never mind then. Yeah, so a larger wire, well, I guess it depends on what you mean by a larger wire. So a wire with a larger cross-sectional area actually has less resistance than a wire of a smaller cross-sectional area. And a longer wire has more resistance than a shorter wire. Kinda, yeah. So I mean, if you had a very long, skinny wire, it would have an appreciable amount of resistance, which would thereby limit the amount of current being able to be transferred from the 9-volt battery to the 1.5-volt battery. Hojun. So basically the same thing. It's just the resistance of the wire is going to be smaller. It's going to be closer to 0, which means it's going to carry more current because there's less resistance to current flow. There's only a finite amount of current that a physical battery can supply. And we'll talk about that a little bit more when we get to talking about practical voltage sources and practical current sources on, oh, let's see. So after nodal and mesh analysis. So I think middle of next week-ish. So like a voltage source a battery or something like that cannot supply an infinite amount of current, whereas one of these ideal voltage sources that we're dealing with in this class can. There's nothing restricting anything, right? So if you were to literally short circuit out a battery, all you're going to see is that the wire is going to get real hot. You're going to see lots of sparks and things are going to start to melt. Way back in the day, and I say that this was 5 or 6 years ago, back when I was teaching the Engineering 120 series, you guys weren't given a battery pack with a barrel jack and all that kind of stuff already attached. You had to solder your own barrel jack onto your battery pack after, I think, about 2 weeks. And so for the first 2 weeks of class, every class, myself and every other Engineering 120 instructor had to remind you, don't put your battery pack in your little bag with the batteries still in it, because if those wires touch each other, the batteries will get so hot that you will melt your battery pack. You'll melt the bag and all that kind of good stuff. And at least 2 to 3 students per quarter would have to go to Miss Ashley and buy a new battery pack because they weren't paying any damn attention and literally melted their stuff down just by throwing it into their bag carelessly with the battery still in it. So batteries can get real hot if you short circuit them and allow them to just drain or transfer as much energy as they have through a small wire. Yeah. All right, so where would be an application where you might see voltage sources in parallel? This is not as obvious as voltage sources in series. So those really fancy Christmas lights are going to have lots of resistances in parallel because of all the bulbs and all that kind of stuff. But what about voltage sources? How many of your parents have solar panels or anything like that mounted to their roofs? Anybody in here? Oh, okay. Well, solar applications are a place where we very regularly place voltage sources in parallel. Okay. Typically, you might see them both in series and in parallel. So let's say that we have this thing is supposed to represent a solar panel, and it generates 12 volts. And let's say that it's rated for 36 watts. And then over here, we're going to have a second solar panel that is identical. It's able of generating 12 volts in direct sunlight and handling power of 36 watts. And we use this to drive some sort of resistive load, which I'm going to call R sub L, right? So we would do something like this, because if our solar panel is rated for 36 watts, our power relationship tells us that each of these solar panels is capable of sourcing 3 amps, which means for every solar panel we connect in parallel, we are increasing the amount of current that we will be able to supply to our load. Now, this is a small scale kind of thing. Some of the work that I do outside of Louisiana Tech is for a company called Sabre Industries out of Bossier City, Louisiana. And I help to design battery energy storage enclosures. And so in those battery energy storage enclosures, we're putting together racks full of batteries connected in series, such that we're getting somewhere between 800 and 1500 volts for an individual rack. And then we're connecting usually somewhere in the ballpark of 20, but up to 50 of those racks in parallel, so that we can output thousands of amps of current, because we are supplying effectively a huge battery pack to supply energy to the grid when there is power outages or something like that, or it's supplemental to That's the battery energy storage component of a solar farm or things like that. Okay? So you tie all those batteries together to be able to output a large enough current to be able to power, I don't know, something like the San Diego Zoo is where we have one of our installations. All that kind of good stuff. So in industry, connecting voltage sources in parallel happens a whole heck of a lot. For home consumer usage, significantly less so. All right, now let's look at current sources. We're going to start with current sources in parallel. So let's say that I have some current IS1 a resistor R through which I'm going to have a current IR arbitrarily flowing down. Let's call this IS2. Let's call this IS3. Like so. I'm going to apply Kirchhoff's current law. Let's do formulation number 1. So currents flowing in equals currents flowing out from the top node. Okay. So on the side, we would have IS1 and IS3. And on the out side of our equal sign, we're going to have IR plus IS2. Rearranging this from the perspective of the resistor, we would see IS1 plus IS3 minus IS2, or effectively, currents in the same direction that are in parallel add together, and currents that are in the opposite direction in parallel subtract. So we could represent this whole thing. Let me put this as IEQ as a single current IEQ connected in parallel to that resistor R. So students typically get a little bit more confused about combining current sources in parallel. I'm not particularly sure why. To me, it seems a little bit easier. If you want your equivalent current source to be up, all of the current sources that are up get a positive sign, all of the current sources that are down get a minus sign. If you want your equivalent current source to be pointed down, all of the ones that are directed down get a positive sign, all of the ones that are directed up get a minus sign. So effectively, you choose what direction you want your equivalent current source to be. Everything in the same direction gets added together. Everything in the opposite direction gets subtracted from that total. Current sources in parallel happen a whole heck of a lot in transistor circuits. It's a thing called a current mirror that we use a whole heck of a lot in amplifier biasing. That's really the only instance that I can think of because you can't really go and buy a current source, quote unquote, off the shelf. And lastly, let's look at current sources in series. So let's say that I have a 3 amp source. Some 10 ohm resistor. And a 3 amp source like so. According to Kirchhoff's current law, IR in this case is simply going to be 3 amps. So effectively, the power burden on each of those sources, once again, gets divided evenly among the two sources in series that are connected to this. So whenever we see current sources in series from a circuit analysis standpoint, it behaves exactly the same if just one of those 3 amp current sources were there and the other one were replaced by a short circuit. Now, if instead we had something like this, applying Kirchhoff's current law here, at this top top left-hand node, we would see that IR is equal to 3 amps. Applying Kirchhoff's current law here at this top right-hand node, we would see that IR is equal to 1 amp. And applying Kirchhoff's current law here at this bottommost node, we would see that 1 amp is equal to 3 amps, which obviously cannot happen. So this is another case where our model breaks down because we're violating the law of conservation of charge in this case. Now, current sources in series, you're going to see even less frequently in the real world than current sources in parallel. In fact, the only instance of current sources in series that I can think of is a cascoded current source, which is a kind of advanced transistor current source that's made where there's just 2 current sources stacked on top of each other in order to achieve a very large output resistance for an amplifier. And I fully understand that practically nobody in this room knows what the hell I'm talking about right now. And most of you won't or at least all of the electricals won't for another 1.5 years or so. Okay. So this isn't something that you're going to see practically ever in practice, and you will never see it again in this class because it just doesn't make any damn sense and we can't analyze anything. All right, so I talked about how we combine all of our different sources. So voltage sources in series, simply add all of the voltages up that are of the same polarity, subtract all of the voltages that are of the opposite polarity. Current sources in parallel, add all the currents up that are in the same direction, subtract all the currents that are in the opposite direction, and then realistically, we shouldn't see voltage sources in parallel in this class or current sources in series in this class beyond today. All right, so any questions about combining sources before we move on to another topic? All right, so a topic that is of much more use. Now we are going to talk about voltage and current division. And this is what you guys' lab is based on today as well, specifically voltage division. So let's start by looking at voltage division, which you guys may or may not realize you've already had a reasonable amount of experience with this concept. So how many times in your engineering 120 series did you generate a circuit like this? Let's call this R fixed. So some fixed value resistance. And then this was some changing resistance, maybe from a thermistor or a photoresistor or something like that. And then you took the output of this network and connected it to an analog input pin of the Arduino. Probably did this multiple times each quarter for different sensors and all of that kind of good stuff. Okay. This is an example of a simple voltage divider circuit where the output voltage in this case was just going to be 5 volts times whatever the value of your variable resistor was. So let me just put this as RVAR divided by R fixed plus R VAR. What we're going to do now is derive why this works this way, and then talk about how we can expand the application of our voltage division relationships to more complex circuits. Okay. So let's say that we have a known amount of voltage at some point in a circuit that contains multiple resistors connected in series. And this should look extraordinarily similar to when we were deriving our ability to add resistors in series. Okay? So I'm going to call this VR1. We'll call the voltage drop across this resistor VR2, and so forth all the way out to VRN like so. I am also going to make an assumption that since there is some total voltage drop across all of these resistors, there is very likely some current flowing through all of those resistors as well. So applying Kirchhoff's voltage law, what we should see is that V known will be equal to I times, actually, let me do this in 2 steps, just so it's obvious. VR1 plus VR2 all the way out to VRN, bless you, or I times R1 plus R2 all the way out to R sub n like so. From this relationship, we could solve for I, and that would just be our known voltage drop divided by the sum of all of those resistors in series. And from this, the voltage drop across any one of our resistors, so I'm going to call this V sub K, would just be I times R sub K, or our known voltage times the ratio of R sub K in the numerator, so the resistor we're interested in finding the voltage drop over, divided by sum of all of those resistances in series. So if we wanted the voltage drop over resistor R1, R1 would be in the numerator. If we wanted the voltage drop over resistor 33, R33 would be in the numerator. The denominator is always just the sum of all of the voltages in series. In a slightly different notation, this is just V known times R sub K over Req, comma S. So that's the equivalent series resistance like we dealt with 2 class meetings ago. So let's put this into practice. So let's say that I have a 10-volt source here. Let's make this an 8-ohm resistor, 5-ohm resistor. Let me make that 5 look more like a 5. And a 12-ohm resistor like so. And let's say that I am interested in determining the following quantities using voltage division. This voltage V5, positive polarity on top. And this voltage V12, positive polarity on the left. So to find V5, that would simply be 10 volts, my known voltage drop across all of my resistors. And the numerator of my ratio is going to be the 5-ohm resistor. And then the denominator is going to be 8 ohms plus 5 ohms plus 12 ohms. So this is going to look like 50 over 25. For 2 volts. So voltage division allowed us to calculate the voltage drop over this particular resistor, or literally any resistor in this series combination, without having to go through the hassle of actually calculating the current that's flowing through that single loop circuit and then applying Ohm's law. So it's just a tool that lets us eliminate a step, okay? Lets us get the answer that we're looking for slightly more efficiently. Now let's look at this voltage V12. So somebody tell me what my equation should look like. 10 volts. All right, so you're 97% correct. So the only problem here is the polarity of the voltage, right? So when we derive all of this kind of stuff, the voltage drops across our resistances were of the opposite polarity of our known voltage. For this V12, our voltage is of the same polarity as our known voltage. So we need to add a negative sign. Another way to think about this, and it's probably a little easier to think about it this way, the current is leaving the positive polarity terminal of our known voltage. When it hits the positive polarity terminal first, we have a positive sign. When it hits the negative polarity terminal first, we have a negative sign. Exactly like we would expect Ohm's law to work based on everything else that we've done in this class. So this is the simple application of voltage division. It does have its uses. Yes, ma'am. Okay, so let's look at exactly what you've suggested. Okay, so our source voltage, we want it to be in parallel with a resistance. So Christina, give me a value for my source voltage. 10 volts. Give me a value for my parallel resistance. So 6 and 24 in parallel. Okay, so here's 6 ohms. Here's 24 ohms. Are there any series resistances that we're concerned with? Okay, so actually, we'll handle that in just a moment. I'm going to answer the question I thought you were asking first, and then I'm going to answer that question because that was exactly what I was going to do in a minute anyway. So let's put a 5 ohm resistor here. And a 7 ohm resistor here. Okay. And let's say for the sake of argument that I'm trying to find the voltage drop across this 7 ohm resistor. How would I do it for this circuit? Patrick, you're looking at things. So you're making life way too hard. Okay, so what is the definition for voltage that we use in this class, right? We talked about 2 different definitions on the secondary class. The first of which was voltage is the work per unit charge required to move 1 coulomb of charge from one point to another in the circuit. That's not the one I'm talking about here. The other definition, what the hell is going on with this thing? The other definition was voltage is the potential difference between 2 points in a circuit, okay? So just for the sake of argument here, I'm going to identify a couple of nodes. So that's one node. And that's another node, right? So the potential difference between the red node and the blue node is 10 volts because there's a 10-volt source between the red node and the blue node. So if I wanted to use voltage division here, I absolutely can. I would say that V7 is simply equal to 10 volts times 7 ohms over 5 ohms plus 7 ohms. So that's going to look like 70 over 12 or 35 over 6 if my mental math is correct. My mental math might not be correct, but the process is. So here's the $1 million question. Why doesn't the 6 ohm resistor or the 24 ohm resistor show up in this equation? Well, we're talking about voltage division. The 6 ohm resistor and the 24 ohm resistor are in parallel with that voltage source, which means the voltage doesn't divide. It's just 10 volts across those 2 particular elements. It only divides when we have a series combination of resistances, okay? Which means only the series combination of resistances should contribute things to our voltage division relationship. Okay. So you're going to see something like this literally today in your in-class assignment. I get so many questions about it. This is the answer, okay? If it's in parallel with the voltage source, it shouldn't be part of your voltage division equation because the voltage isn't divided. All right, now let's circle back around to Christina or Isaiah. Do you have a question? Yeah. So that's exactly what we're going to look at here for this example. So Isaiah, you give me a value for a voltage source. 12 volts, okay? Then I'm going to put a resistor here. Somebody call out a number. 7, okay? I'm going to put a resistance here. Somebody else give me a number. and I'm going to put a resistor in parallel with that 20 ohm resistor. Somebody give me a number. 3. Okay. So let's figure out what this voltage is, which I'm just going to call Vx, representing the voltage drop across the 20 ohm resistor and the voltage drop across the 3 ohm resistor, because they're in parallel, they have to be the same thing. And I'm also going to find the voltage drop across the 7 ohm resistor here. So let's start with the voltage drop across the 7 ohm resistor. So I'm going to have 12 volts, which is my known voltage. In my numerator, I'm going to have the 7 ohms, because that's always the resistance that I'm trying to find the voltage drop over. Anybody have any idea what my denominator is supposed to look like here? So the 20 and 3 in parallel, but there's something else too. Plus 7, yeah. So 7 ohms plus 20 ohms in parallel with 3 ohms. So effectively, in order for voltage division to work, we need to make the circuit look like it's just a bunch of resistors in series. So that 20 in parallel with 3 can be combined into a single resistance that then satisfies that we have a known voltage being dropped over several resistors in series. Okay. And this will come out to whatever the heck it comes out to. I'm not particularly worried about it. If we wanted to figure out Vx, well, that parallel resistance would be in our numerator, right? So we'd have 12 volts times 20 ohms in parallel with 3 ohms divided by 7 ohms plus 20 ohms in parallel with 3 ohms. And then we throw that into our calculator. So that's how voltage division can be applied to networks that don't technically meet the criterion, but as long as we can make the resistors look like they're in series, they'll still work. So any questions about voltage division? By the way, I'll be doing stuff like this constantly, and you'll see it pop up in your homework assignments and all that kind of jazz too. Exactly right. Which is why, so they will have the exact same voltage drop, which I'm calling Vx. And because they have the same voltage drop is why I'm treating it as if it were a single equivalent resistance taking that place. Because if I replace the 20 and the 3 with, let's see, 60 over 23, what changed? Nothing. Same current is leaving the positive polarity terminal of my voltage source, so it's delivering the same amount of power and all that kind of stuff. Those two circuits are electrically equivalent, so the relationship should be the exact same thing. Okay. All right, any other questions regarding voltage division? Okay. All right, so now let's talk about current division. And I'm going to go ahead and preface this by saying that I teach this significantly differently than every other teacher that teaches circuits at this school. So if you had, that's not how you spell current, a different teacher for circuits before, in my very conceited and biased opinion, they did it wrong. All right. So let's say that we have a network of resistances connected in parallel. Let's call this R1. This R2. And this R sub n. because all of these resistors are in parallel, they should have the same voltage drop over them, which I'm just going to call V. And let's say that there is a known amount of current flowing into this network containing all of these resistors in parallel. I'm going to define each individual resistor current in the down direction, effectively saying that my known current is going to split up or divide among these resistors. And we are going to develop a relationship that tells us how that division takes place. Okay. So if I apply Kirchhoff's current law, I could say that my known current, I known, is equal to IR1 plus IR2 all the way out to IRN, like so. And now I'm going to use Ohm's law to express all of those resistor currents in terms of my voltage V. So that's going to look like V divided by R1 plus V divided by R2 all the way out to V divided by R sub n. And what I'm going to do now is I'm going to rearrange this thing and solve for V. And so what I should get is my known current divided by one over R1 plus one over R2 all the way out to 1 over R sub n. I can then say that the current flowing through my kth resistor is V divided by R sub k, or V times the reciprocal of R sub k. And what that's going to let me do is I'm now going to have that current I known times the ratio of 1 over R sub k divided by 1 over R1 plus 1 over R2 all the way out 1 over R sub n. So it looks extremely similar to our voltage division relationship, except that we're using the reciprocals instead of the resistor values directly. Now, the reason why I teach current division this way, as opposed to the way that the other professors teach it, is because this expression can be used for any number of resistors connected in parallel, whereas the other relationship that is commonly taught can only be used for exactly 2 resistors in parallel. And we are going to have situations where we need to be able to deal with more than 2 resistors. Okay. So, to put this in a slightly different form, this is just the ratio of our known current, known current times the ratio of the equivalent parallel resistance divided by the resistor we're interested in. Because 1 over R1 plus 1 over R2, etc., is just REQ in parallel. So let's apply this. So let's say that I want the current flowing down through the 3 ohm resistor and the current flowing up through the 1 ohm resistor. What should my equations look like? Let's start with the 3 ohm resistor, right? So I3 should be what? Literally apply this equation to the circuit. What's my known current? 4 amps. What should be in my numerator? 1 over 3 ohms. What should be in my denominator? Absolutely right. And then we would throw this into our calculator and get a number. I'm not concerned with the number. I'm concerned about teaching you guys the process. Okay. If we were trying to solve for the current I1, what would our equation look like? So it's going to be practically the same relationship, except that we would replace the 1 over 3 ohms in the numerator with 1 over 1 ohm, because we're now interested in the current flowing through the 1 ohm resistor. So you're correct there. What other change needs to be made? We need to include a negative sign because the current is flowing in the opposite direction that we would expect current division to occur, right? So when we derived things here, the known current was flowing in and all of our resistor currents were flowing out. In this network, the known current is flowing in and I1 is flowing in, so we need to include the negative sign there. Another way to think about it is that if all of these have the exact same polarity, voltage, if all of these share a voltage V, positive polarity on top, the current I1 is flowing into the negative polarity terminal, which means we need to include a negative sign. Carrie, how may I help you? 4 amps. Sorry, thank you for that. Me getting lazy with units. So this is simple application of current division. Now let's mess things up. So I'm going to do one example here that's going to have 2 things in it to kind of mess with you. Let's do 5 amps here. Put a 3 ohm resistor here. 7 ohm resistor here. 2 ohm resistor here. And a 10 ohm resistor here. And I want us to apply current division. Find this current I sub 10. So the first question that you are likely asking yourselves is, well, how the hell do I apply current division to this? Because this isn't just a bunch of resistances in parallel. So let's talk about the 3 ohm resistor thing first, okay? How much current flows through the 3 ohm resistor? 5 amps. So the network that we are going to apply current division to is really just everything to the right of this red dashed line, because we know that 5 amps is flowing into this network. So we're trying to figure out how much of that 5 amps of current flows through that rightmost branch. So, nailed it. So we would say I10 is going to be 5 amps. So the total resistance of the branch that we're trying to find the current through is 1 over 2 ohms plus 10 ohms, or as Christina suggested, call it 12 ohms, easy enough. And then our denominator would look like 1 over 7 ohms plus 1 over 2 ohms plus 10 ohms. So all we're doing here is using equivalent resistances to make it look like there is a known current flowing into a network containing resistors in parallel. Just like we use equivalent resistance with voltage division to make it look like there is a known voltage drop over a bunch of resistances in series. So we can vary our resistor combination techniques inside voltage division and current division to be able to apply these techniques to more complex networks. All right, so that is enough ranting out of me for today. Unless anybody has any questions, Ian, how may I help you? So we can skip the 3 ohms, actually. So let me put it in context here. I can skip the 3 ohms, just like I can skip this 6 and this 24. The current doesn't split if it's in series, just like the voltage doesn't split when these resistors are in parallel. Great question. Any other questions? Resistors aren't in parallel. That's it. And you can't use voltage division if resistors aren't in series. That's about the gist of it. In order to apply these techniques, you need to know that for voltage division, you need to know the voltage drop over a series or series combination of resistors. In order to apply current division, you need to know the current flowing into a parallel combination of resistors. If you have that information, it can be applied. If you don't, it can't. Yes, you're going to see that whole heck of a lot of you suffer through something. Yes, yeah, you're going to suffer through something, and then you're going to learn something that was going to make what you were doing much, much easier. Yep. All right. Yes. So if you don't know the voltage drop across the resistors in series, or you don't know the current flowing into the resistors in parallel, then you can't apply it. So it requires you to know the voltage or know the current. How you figure that out is kind of up to you. Yeah. All right. Any other questions, or are we doing mini lab and or in-class assignment? All right, go nuts.